In this lesson, we're going to be identifying characteristics of quadratic functions, and we're going to be graphing and using quadratic functions of the form f of x equals ax squared. A quadratic function is a nonlinear function that can be written in the standard form of y equals ax squared plus bx plus c, where a does not equal 0. The U-shaped graph of a quadratic function is called a parabola. In this lesson, you will graph quadratic functions where b and c equal 0. I'm going to scroll down here. Characteristics of quadratic functions. The parent quadratic function is f of x equals x squared. The graphs of all other quadratic functions are transformations of the graph of the parent quadratic function. The lowest point on a parabola that opens up, or the highest point on a parabola that opens down, is the vertex. The vertex of the graph of f of x equals x squared is 0, 0, or the origin. The vertical line that divides the parabola in two symmetric parts is the axis of symmetry. The axis of symmetry passes through the vertex. For the graph of f of x equals x squared, the axis of symmetry is the y-axis, or x equals 0. So here we have our parabola. Okay, so right here, from left to right, the y value is decreasing, and then when it gets to the vertex, right here, the lowest point, the y value is increasing. Okay, this right here, this line is the axis of symmetry, and that just means that it is symmetrical on either side of this if you're at the same y value. For example 1, consider the graph of the quadratic function. Using the graph, you can identify characteristics such as the vertex, axis of symmetry, and the behavior of the graph as shown. All right, so that's what we're going to do. We're just going to identify some characteristics of this graph. The first thing that I would recommend looking for is always the vertex. Okay, the vertex is going to be either the lowest point if the graph opens up like a cup, or the highest point if the parabola opens down like a frown. Okay, anyway, this is up like a cup. So I see right here, that's going to be my vertex, okay, because this is the lowest point. And that's at the ordered pair -1, -2. So I'm going to write that down. I'll just draw that point in there. Okay, and then once you find the vertex, you've also essentially found the axis of symmetry. Remember, the axis of symmetry is the vertical line that breaks up the parabola into two symmetrical parts. Okay, so this line right here is the axis of symmetry. And this is at the x value, -1. So my axis of symmetry, I'm just going to write AOS for axis of symmetry. That's going to be the equation x equals -1. If I just graph that as a quick sketch, a dotted line here, we know that every single point over here is the same distance as every single point over here from this axis of symmetry. Now we need to describe the behavior of the graph. Okay? Well, remember, we always want to look from left to right as we are increasing our x value. Okay? So on the left side of my vertex, so when x is less than -1, we can see that from left to right, my graph is going down. So this function is decreasing when x is less than -1. So when x is -1, the function is decreasing. And then when x is greater than -1, we see that the value from left to right of y is going up. Okay, so that means when x is greater than -1, this function is increasing. Anyway, we have successfully identified the vertex, axis of symmetry, and we've described the behavior of this parabola, and now we're done with example 1. Graphing and using f of x equals ax squared. When 0 is less than a is less than 1, the graph of f of x equals ax squared is a vertical shrink of the graph of f of x squared. When a is greater than 1, the graph of f of x equals ax squared is a vertical stretch of the graph of f of x equals x squared. And that makes sense because over here I'm multiplying by a number that's smaller than 1, so I'm going to be shrinking it down towards the x-axis. And then over here I'm multiplying my output by a value larger than 1, so I'm going to be stretching it out away from the x-axis. Okay, now down here, when -1 is less than a is less than 0, the graph of f of x equals ax squared is a vertical shrink with a reflection in the x-axis of the graph of f of x equals x squared. Okay, and that makes sense because now I would have a negative coefficient on my parent function, and that coefficient would be less than 1. The absolute value, I should say, the absolute value of that coefficient would be less than 1. Okay, so I'd be shrinking it down, and the negative sign means I would reflect it in the x-axis. When a is less than -1, the graph of f of x equals ax squared is a vertical stretch with a reflection in the x-axis of the graph of f of x equals x squared. So same logic there, but now that my absolute value of my coefficient would be larger than 1, I'm stretching it away from the x-axis, and the negative sign means that I am reflecting it in the x-axis. In this example, we're going to graph the function g of x equals 2x squared, and then compare the graph to the graph of f of x equals x squared. Well, I always say whenever we're graphing and feeling unable, we should make a table. Okay, so we're going to make a table of values. So first I'm going to graph g of x, which is 2x squared. Okay, so I'm going to have my x value, and then g of x. And I usually like to have at least 5 points when I'm making a parabola. If you can fit more, then I would recommend doing that. But 5 is going to be pretty much the minimum that you want. So I'm going to make spaces for 5, and we'll see if we can fit more. Okay, and you always want your vertex in the middle. Now, for all of these graphs, because we're dealing with b and c equaling 0, we just have f of x equals ax squared. In this case, g of x equals ax squared. Our vertex is always going to be 0, comma 0, the origin. Okay. In later sections, we'll look at when the vertex is not 0, and I'll teach you guys how to do that. But for now, I'm going to know for a fact that 0, 0 is going to be my vertex. So 0, 0, okay? And then I'm going to plug in points around this. So I'm going to do 1 and 2, and then -1 and -2. Now, since I know my vertex, and I know that my axis of symmetry goes through my vertex, whatever y value or output value goes here, the same distance away from my vertex, is going to be the same one as here, which is why I recommend starting with your vertex. Okay, so if I plug 1 into this function, 1 squared is 1 times 2, well, that's 2. Okay, well, if I plug in -1, it's symmetrical, so this is also going to be 2. Okay, and you can do that math out if you wanted to. And then if I do 2, I get 2 squared, which is going to be 4, and then I multiply that by 2, I get 8. So we get 8 here, and same thing, this is symmetrical, so this one's also going to be 8, and you could also plug that in if you wanted to. So now I'm going to plot these points for g of x, and I will do that in blue. All right, now we want to draw a smooth curve in the shape of a parabola, which you've seen in the last example, that goes through all these points. I would recommend, whenever you're sketching a curve, to try it in multiple sketches rather than doing it in one, because if you do it in one try, it might not be perfect. Anyway, it looks better with a pencil and paper, but I'll do my best with the stylus here. So something like this, you can see that I tried to make this as curvy as possible here. And don't forget your arrows, because the y values of this graph are going on infinitely. Anyway, we've successfully graphed g of x, but now we want to compare this to the graph of f of x. So I'm going to graph f of x as well. And I'm just going to make another row in my table. So f of x. Okay, and then once again, I know the vertex is going to be 0, comma 0, the origin. And then I'm just going to plug my values in. Well, if I plug in 1 for my x value, f of x is just going to be 1, because 1 squared is 1. And then same thing here, it's symmetrical. And then if I plug in 2, 2 squared is 4. So this will be 4, and this will be 4 as well. Okay, I'm going to graph this one in pink. So my vertex is going to be the same, but now I have this point and this point. And I can also fit 3 for an input, because 3 squared is going to be 9. I'm not going to do that on my table, but that's going to be right there. And that means I can fit -3 as well. Anyway, I'm going to draw my smooth curve through here. So obviously this is not perfect, but it's good enough for a sketch. If you wanted a perfect graph, you would use a computer or some sort of digital tool to help you do that. Anyway, now we need to compare these graphs. We've graphed them both, now let's compare them. Well, if you notice, I have a 2 being multiplied by my parent function. My parent function is x squared, and now I'm just multiplying it by 2. Okay, and I would call this the outside of the function, because it's not like the 2 is in parentheses. If it was something like this, y equals 2x quantity squared, this would be the 2 on the inside of the function, but the 2 is on the outside because the x squared is happening and then the 2 is being multiplied after. So anytime we have that, that is going to be a vertical stretch of a factor of 2. So if I look at my points from the pink graph to the blue graph, I see that my output here is 1, and then I double it here, so that's 2. Then I see my output here is 4, and then on the blue graph, I double it again. That goes from 4 to 8. Okay, so basically you can think of the pink graph, we're just stretching it out. We're pulling it away from the x-axis and stretching it by a factor of 2. Okay, so this is going to be a vertical stretch by a scale factor of 2. So we've successfully graphed both of these functions and compared them, and now we're done with this one. So in this example, we're going to graph h of x equals negative 1/3 x squared, and then compare it to the graph of f of x equals x squared. So this is similar to the last example that we just did. So I'm going to make a table of values. So I have x, and then h of x. I'll do my values here. And I see that I'm counting by 2's instead of 1's in my axis, so I might count by 2's here. So I'll put 0 in the middle. And, I think I'm going to be able to fit more because I see that my coefficient is negative 1/3. So I'll start right here for 0, and if I can fit more, great. If I can't, no worries. Anyway, so 0, 0 will be my vertex. And then I'm going to plug in 2 for x. So if I plug in 2 for x, 2 squared is 4. 4 times negative 1 is negative 4/3, which is the same thing as negative 1 and 1/3. And then I'll try 4 here. If I plug in 4 for x, I get 4 squared is 16. And then negative 1/3 times 16 is negative 16/3, which is the same thing as negative 5 and 1/3. I'm going to try 6, see if we can do 6. 6 squared is 36, and then negative 1/3 of 36 is negative 12, so that actually will fit on this graph. All right, and then all I have to do over here is just put these values and then negative 2, negative 4, negative 6, because remember, this axis of symmetry tells me that the output for 2, since 2 is the same distance away from 0 as negative 2, will be the same as negative 2. So this will be negative 1/3, 1 and 1/3, I should say. This will be negative 5/3, 5 and 1/3, I should say, then negative 12. So negative 2, negative 4, and negative 6. So now I'm going to plot all these points. I'll do these ones in blue. Now I'm going to sketch my parabola through these points. So something like that. Now I'm going to graph my parent function, f of x equals x squared. So I'm just going to make my table here. Add another row, I should say. So I'm going to have f of x, and then that'll be 0, and then 2 squared is 4, and then 4 squared is 16, and that's not going to fit on my graph, which is fine. Anyway, I'm going to plot my points in pink to compare. So my vertex is the same, and then I see that I have the point 2, 4, and that's all that's going to fit on this graph. So I'm going to draw a smooth curve through this. So something like this. Anyway, now we're going to compare these two functions. So I see that there's a reflection here because my original parent function is up like a cup, and then this one's down like a frown. And then I see that this one is a bit wider, okay? Or another way you can think of it is that we've smushed it down towards the x-axis. We've shrunk it down. And that makes sense. If I look at my equation, this coefficient is negative, and the absolute value of it is less than 1. So it's going to be a vertical shrink, and that scale factor is going to be 1/3. And the negative sign outside means that there's going to be a reflection, and that reflection is going to be a vertical change, which means it's a reflection in the x-axis. The x-axis is acting as a mirror. So my transformations are going to be reflection in the x-axis, and then vertical shrink with a scale factor of 1/3. All right, so these are my transformations, and we've successfully graphed our functions, and now we're done with this one. For this example, the diagram at the left, or actually below because I moved it, shows the cross-section of a satellite dish where x and y are measured in meters. Find the width and the depth of the dish. So I have this function y equals 1/4 x squared, and all I need to do is find the width and the depth of the satellite. Well, you can use your function to figure this out, but actually the graph's going to be much easier. Okay? Well, I know that the satellite stops at this point when x is 2 and y is 1, and this point. So the width of this is just going to be the distance between this and this. And you can easily tell that that's going to be 4 because I'm going from -2 to 2. So the width of this is going to equal 4, and it's measured in meters, so 4 meters. And then now I want to find the depth. Well, I see that going from my vertex, which is at 0, 0, to this right here, is going to be just 1 meter. So the depth is going to equal 1 meter. So using the graph, we've successfully found the width and the depth of our satellite, which is in the shape of a parabola, and now we're done.